In this video, we are starting our section on polar coordinates. So there are many types of curves out there where it can be simpler to express them using a different type of coordinate system. So I can express points in the plane using a new type of coordinates called polar coordinates. And this will make the process of evaluating certain integrals much simpler. So our goals in this section are to convert between our regular Cartesian coordinates and these new polar coordinates to sketch regions given to us in polar coordinates and to recognize when and how we can evaluate double integrals using polar coordinates. So in this video, we will talk about what polar coordinates are. So a point P can be described in Cartesian coordinates, which are sometimes called rectangular coordinates, as x comma y. And this is likely what we're used to. So if I have a point here, I can call it x comma y. These are Cartesian coordinates. What we're going to learn about now is a new type of coordinates called polar coordinates. So polar coordinates, in polar coordinates you keep track of r and theta, where r is the directed distance from the origin to the point. So if I have my point here, r is the distance from the origin to that point. Okay, and theta is the directed angle from the positive x-axis. So if I measure this angle from the positive x-axis to this line, that's theta. All right, so let's do an example. So let's find the polar representations for the point x comma y, which is 2 comma 2. So this is given in Cartesian coordinates or rectangular coordinates. So let's draw a graph. So I'll draw my axes. Let's draw our axes. I can draw this point 2 comma 2. So I'll have this point, and so I know this is 2, and I know this is 2, and I'm going to connect to this point with the origin, and then drop this perpendicular line to the x-axis to make a right triangle. So in my picture, this horizontal length is 2, and this vertical length is 2. Okay, and I want to express this in polar form, so I need r and I need theta. So r is going to be the distance from the origin to this point. So I could use Pythagorean theorem for that, or I could use some of my special right triangle stuff. But it turns out that if you do that, the value of r is 2 root 2. Okay, so r is going to be 2 root 2. And then because these two sides are the same, that means these two angles are going to be the same. So they both have to be 45 degrees, which in radians, that's pi over 4. So theta is pi over 4. All right, so I got my value of theta, which is pi over 4. Okay, and I've just converted this point in rectangular form or Cartesian form to polar form. But it turns out this isn't the only way that I can express it in polar form. There's multiple ways to do this. So let's talk about another way. So I'm going to extend this radius line, but in the opposite direction. And instead of measuring the angle as I did, I'm going to measure the angle all the way up until this spot here. So that new theta would be 5 pi over 4. And if I now took a value of r, some positive r value, that would be going this way. But if I took a negative value of r, I would be going the opposite direction. And this is what the term directed distance means. Based on what theta is, if theta is 5 pi over 4, if I now go in that direction along that line, that's a positive r value. But if I go in the opposite direction from there, that's going to be a negative r value. So I could also do this if I let my angle be if I let it be 5 pi over 4, but I let r now be negative 2 root 2. Okay, and there's many other ways to do this, because I could start at this angle pi over 4 and then go around the unit circle one full time. I could add 2 pi to it. Or I could go around again and add 2 pi again and be at that same spot. So that would give me the r value 2 root 2, but the angle could be pi over 4 plus 2 pi k, where k is an integer. And what that's saying is I could keep adding multiples of 2 pi to keep going around the circle again and again and again, but being at the same spot. We could do the same thing for this point. I could take that negative 2 root 2 for r, and then take that angle 5 pi over 4, and then add to it 2 pi k, multiples of 2 pi. And I want to mention that, this includes the possibility where k is negative, because that would be going around the unit circle, but in the opposite direction, which is totally valid. Okay, so it turns out that these represent all the types of polar representations for this point. So polar representations, there aren't just one. They're not unique, which is something interesting about them compared to Cartesian coordinates. All right, so what I want to end by talking about are some equations that I can use to convert between polar to Cartesian. So if I go to my picture and I use some trig in the picture, I see that if I did cosine of theta would be adjacent over hypotenuse. So that's going to be x over r. And if I did sine of theta is going to be opposite over hypotenuse. So that's y over r. So y over r. And if I take these equations, and now I know I multiply both sides by r, I can isolate and get x equals r times cosine theta, and y equals r times sine of theta. So with these equations, if I know the polar coordinates, if I know r and theta, I can plug them in here and then figure out what x and y had to be. I can convert it to Cartesian form. I could also go in the other direction, but to do that I need some new equations. So if I did Pythagorean theorem here, it would give me that r squared equals x squared plus y squared. And then to get something with the angle, I could do tangent of theta. That would be y over x. So with these, if I know x and y, if I know the Cartesian coordinates, I can plug them in and then use them to figure out what r and theta are, to convert to polar form. So in terms of our goals for this section, we finished the first goal, talking about how we can convert from Cartesian form to polar form. In the next video, we'll learn how we can sketch regions and curves that are given to us in polar coordinates.